Conceptual Introduction to Linear Regression, Part 2, P-values for the slope and intercept. Here's a plot of two variables with their linear regression line drawn in blue. The units don't matter, this is hypothetical, but the axes are shown so you can see where 0 is. Does the intercept seem to be different from 0? A tiny bit, but basically no. The points that have x values close to 0 seem to have y values centered around 0. That is, the points in the middle horizontally are just as likely to be up or down vertically. And the regression line crosses the y-axis very close to 0. But not exactly at 0. It's clearly very slightly above 0, and that very slight difference is a coincidence. These are just random points generated by a process that scatters them evenly, and it happened to result in a line with a very slight positive intercept. Does the slope seem to be different from 0? Again, a tiny bit, but basically no. The points with higher x values do not seem to have higher or lower y values on average. That is, the points on the right do not seem to be higher or lower on average than the points on the left, and the regression line is almost horizontal. But not exactly horizontal. It clearly has a very slight negative slope. That very slight negative slope is a coincidence. These are just random points generated by a process that scatters them evenly, and it happened to result in a line with a very slight negative slope. How about here? The slope is exactly the same as before, but this line has a much larger positive intercept. This positive intercept is clearly not just a coincidence. In fact, only 2 of the points have negative values of y. Most of them are way above the horizontal axis. These points clearly came from a data-generating process that is much more likely to create positive rather than negative values of y. Finally, check out this example. Where's the intercept? It's clearly positive. There are plenty of negative values of y, but they're all on the left, not near the middle. The values of x that are close to 0 all have values of y that are well above 0. The blue regression line crosses the y-axis well above 0 as well. The intercept is clearly positive, not just due to a coincidence, but due to a process of generating points that was more likely to create positive y values when the x values were near 0. How about the slope? It's also clearly positive. The points with higher x values have much higher y values on average than the points with lower x values. That is, the points on the right are higher on average than the points on the left. The regression line points upward as you trace it from left to right. Could this positive slope have resulted from points generated by a process that scatters them evenly, and it just happened to result in a bunch of extra points in the upper right and lower left? No way. We haven't done any math on it, but it is clearly too extreme to be a coincidence. The process that generated the x values must have been associated with the process that generated the y values. Or rather, it doesn't have to have been associated with the process that generated the y values. But if these processes were independent, the data that we're seeing on the screen right now would be extremely unlikely to arise. So we would like to be able to argue that the slope on the left is only different from 0 due to a coincidence, that it could plausibly arise from a data-generating process where x and y are independent. And we would like to be able to argue that the slope on the right is not like that. It would be very unlikely to arise from a data-generating process where x and y are independent. This should remind you of the reasoning behind p-values from a couple of weeks ago. Here are 20 sets of 100 data points, with 2 variables each, plotted with a linear regression line. All of these data sets really were generated from a random process where x and y were independent. You can see that some of these slopes are steeper than others. They don't all look totally flat. That's what happens when we're dealing with randomness. So we can't just rely on the line being visually angled to say that it is statistically significant. We would fool ourselves too easily that way. If I do an experiment and obtain a single regression line for my 2 variables of interest, I want to get a p-value for the slope. I will want to test the hypothesis that the slope is different from 0. In other words, I want to know if a data-generating process where x and y are independent would have been very unlikely to generate data like mine. By convention in psychology, we often call p-values less than 0.05 statistically significant. All of the data sets on the screen really were generated from a random process where x and y were independent. So how many of them would we expect to have p-values less than 0.05? one of them. Not necessarily exactly 1, but one of them on average, because 0.05 is the same as 1 out of 20. And sure enough, this one has a p-value of 0.04. Most of the time, when we call something statistically significant, we're hoping that it is more extreme than this, extreme enough that if it was a coincidence, it would happen less often than 1 out of 20 times. How does the computer get p-values for these slopes? It turns out that we can characterize the distribution of slopes that would be generated by a random process like this, and then calculate p-values based on that characterization of the distribution. This is a normal distribution. It's a decent way to describe the possible slopes that we could get from a data generating process where x and y are independent and we have a sample size of 100. I've drawn a vertical gray line at 0. Most of the time, the slope will be close to 0. On rare occasions, we get a fluke slope that's farther away from 0. I didn't show units on the x-axis here because, of course, it would depend on the units of our variables. But the linear regression calculations also give us a standard error for our slope. That is an estimate of the standard deviation of this kind of distribution, the distribution of possible slopes in experiments like ours, if the null hypothesis was true. When we take our actual slope and divide it by its standard error, we get a t-value. Here is a t-distribution with 98 degrees of freedom. It looks very similar to a normal distribution. The t-value we get by dividing the slope by the standard error is one possible value from this t-distribution. And we can get a p-value by figuring out how unusual that possible value would be if it was generated from this t-distribution under the null hypothesis. This is what a p-value of 0.05 looks like in this t-distribution. The area under the values more extreme than approximately 2 is shown in red. We expect to get values this extreme around 1 out of every 20 experiments if the null hypothesis is actually true. Here are values more extreme than 3, cases where the slope is more than 3 times the standard error. This corresponds to a p-value of 0.0017. We only get values this extreme in around 2 out of every 1,000 experiments, if the null hypothesis is true. So when we find a slope that we think looks interesting, we use the p-value to see if it is extreme enough that it would probably not happen very often in a universe where the variables were independent. I'll come back to this idea.